Hi guys! Welcome back to Budget Power Electrical Solutions. In this episode, we're going to understand the current time trip curve of a thermal overload relay. An overload relay does not trip based only on current. It also depends on how long that current continues. During motor starting, current can be very high for a short time, but the relay must allow the motor to accelerate without unnecessary tripping. So the key question is, how much current, for how long? Let's look at the trip curve and understand what it really tells us. Now let's look at the actual overload relay trip current curve. On the horizontal axis, we have the current multiple, based on the relay setting, or IR. On the vertical axis, we have the trip time in seconds. The important thing to notice is the shape of the curve. When the overload current is only slightly above the relay setting, the relay allows a longer time before tripping. But as the current becomes higher, the trip time becomes much shorter. For example, if the relay is set to 60 amps, then 2 times IR means 120 amps, and 6 times IR means 360 amps. So always remember, higher current means shorter trip time. In the next slide, we'll see exactly how to read a trip time from this curve step by step. Now let's make this curve easy to read. First, look at the x-axis. This shows the current as a multiple of the relay setting, IR. Then move vertically upward until you reach the trip curve. From that point, move horizontally to the left and read the trip time on the y-axis. For example, at around 2 times IR, this example curve gives a trip time of approximately 0.3 seconds. But at only around 1.2 times IR, the trip time is much longer. So the method is simple: choose the current multiple, go up to the curve, then move left to find the trip time. Once you understand this, reading overload relay curves becomes much easier. Now we come to a very important idea: inverse time operation. Inverse time simply means that a small overload is allowed for a longer period, while a large overload causes the relay to trip much faster. Why does this happen? Because motor heating depends on both current and time. A slight overload creates heat more slowly, so the relay allows some time. But a severe overload creates heat much faster, so the relay must respond quickly to protect the motor. This is very useful in practice, because the relay can tolerate normal short-duration conditions while still reacting quickly to dangerous overloads. So remember, more current means more heating, and usually a shorter allowable trip time. Now we need to understand IR, because every point on the trip curve is based on this setting. IR is simply the overload relay current setting. For example, if we set IR to 60 amps, then 1 times IR is 60 amps. 1.2 times IR is 72 amps. 2 times IR is 120 amps. 4 times IR is 240 amps. And 6 times IR is 360 amps. This is why you cannot read a trip curve correctly unless you first know the relay setting. The same curve can represent different actual current values depending on the selected IR. So before using the curve, always confirm the correct current setting on the overload relay. Now let's compare trip class 10, class 20, and class 30. The main difference is how long the relay allows a high starting current before tripping. Class 10 responds fastest. Class 20 allows more starting time. And class 30 allows the longest starting time of these 3 examples. That means class 10 is commonly suited to motors that accelerate quickly, such as pumps or fans. Class 20 can be useful for motors with a medium starting time, such as some conveyors or compressors. And class the 30th may be used where the motor has a heavy load or high inertia and needs more time to accelerate. The important point is not to simply choose the slowest class. We should select the lowest trip class that still allows a healthy motor start without nuisance tripping. Now let's connect the theory to a real motor example. Suppose the motor full load current is 60 amps. During starting, the current reaches approximately 6 times FLA, which gives us about 360 amps. And let's say the motor needs around 12 seconds to accelerate. Now we plot this motor starting point on the time current curve. Our selected trip curve must allow the motor to pass through this starting condition without tripping. If the curve crosses below the motor starting point, the relay may trip before the motor finishes accelerating. In this example, if the starting time is close to 10 or 12 seconds, class the 20th of may provide more starting margin than class 10. But the final selection should still be based on the actual motor, starting time, load, and manufacturer data. Another important point is the difference between a cold curve and a hot curve. A cold relay has not been heated by previous motor operation, so it can usually tolerate an overload for a longer time. A hot relay is already warm. Because it already has stored thermal energy, it may trip much sooner under the same overload condition. This becomes very important when a motor is started repeatedly. After one start, the overload relay may still be warm. If we immediately restart the motor, the next starting current may cause the relay to trip earlier than expected. This is called thermal memory. So in real applications, repeated starts and hot operating conditions must be considered, not only the cold trip curve. Now let's bring everything together and make the final practical selection. First, verify the motor nameplate full load current. Second, choose an overload relay whose adjustable current range includes that motor current. Third, select the correct trip class based on the motor starting time and application. Then set the overload relay current, IR, to the required motor value according to the approved setting method. For example, if the motor FLA is 60 amps, the selected overload relay must include 60 amps within its adjustable range. The brand may be Schneider, Siemens, ABB, Allen Bradley, or another suitable manufacturer. The important points are the current range, trip class, mounting compatibility, reset method, and manufacturer recommendations. And remember, setting too low can cause nuisance trips, while setting too high can reduce motor protection. Finally, after selecting and setting the overload relay, we need to commission the system properly. First, verify the motor nameplate FLA. Start the motor and make sure it accelerates normally. Then measure the running current with a clamp meter and compare it with the expected value. Make sure there is no nuisance trip during a healthy start. If a safe test method is available, confirm that the overload relay trips correctly under an abnormal overload condition. Then record the final IR setting, selected trip class, relay model, and motor details. This final step is very important because good protection is not only about choosing the correct relay. It is also about setting it correctly, testing it, and documenting the final values. That gives us healthy motor starting and reliable overload protection. And in the next final project, we can take a real industrial motor and go through the complete overload relay selection process from start to finish.